Hello, good morning everyone. I am B. Kashim Basha from the Department of Electronics and Communication Engineering studying at VITAP University. Today I am presenting my final project titled EV ADAS System with Real-Time Dashboard. My presentation is divided into three parts. In the first part, I will explain the overall EV ADAS system, including its design and working. In the second part, I will explain the real-time dashboard which displays the vehicle information and safety alerts. And in the third part, I will show you the outputs and the how I executed overall project. So without any late, let's begin the presentation. Here we have EV ADAS system, and in system scope, we have the project focuses on developing a smart electric vehicle, monitoring the system integrated with advanced driver assistance system features. The main goal is to improve both vehicle monitoring and driving safety. We have our system continuously monitor important vehicle parameters such as speed, battery life, monitor temperature, motor temperature, torque, and driving range. Along with monitoring, it provides safety features like collision warning, blind spot detection, and parking assistance. If any fault or dangerous situations occurs, the system immediately alerts the driver and shifts the vehicle to the safe state. These are all the system scope, and we have the stakeholders key use cases. Here we have EV dashboard monitoring operates observes like speed and torque range. All these comes under the motor temperature range. All this comes under the EV dashboard monitoring. And we have forward collision warning. We have which we calculates with the distance between our vehicle with the forward vehicle is comes under the forward collision warning. And blind spots we have two, where it's left blind spot and right blind spot. We detect both the blind spots, and if it's close, any vehicle comes too close to our vehicle, then it comes under it's treated as the fault, and we have the alarms. And then functional requirements, we have EV controller, ADAS engine, fault and safety. We used an UART telemetry communication protocol. We have everything, radio acceleration pedal, estimating SOC, remaining range of power. We can calculate how much battery we have, and with that battery, how much distance we will have to cover. It will also shows everything. ADAS engine monitoring, if there is a temperature increase or not, motor temperature, engine temperature is increased or not. And it's also calculate the TTC, which means the time to collision. If it is any vehicle is coming to collide with our vehicle, then it is other vehicle is close less than 50 centimeters, it warns, and with less than 30 centimeters it detects and it stops our vehicle. These like safety systems are there in our project. The non-functional requirements, here it is designed to work in real time with fast response, accurate sensing, and reliable communication so that warning are generated without any delay. Here delay is not there because we calculate here 5 milliseconds takes to control loop. Main EV loop execution time is this. That means our code, our sensing is taking real-time data with 5 milliseconds of time. We calculating that much fast sensing so that we cannot have any delay with the we can get real-time accurate data. Because we are doing it fast means sensing fast means we will decrease the response time and all everything will response will be higher fast. And sensor pole also 100 milliseconds, and we have UART latency 10 milliseconds. Because we have to communicate, right? We have to send data, it will take 5 milliseconds delay. Distance accuracy plus or minus 30 millimeter. Sensing and all real time fault state entry latency, one loop cycle from detection. And communication we have UART bond rate 115200 bps, 18.1. Sensing ADC resolution 12 bit. We have lot of range sensor polling in traveling 100 meters of sensing. And then we have system architecture and data flow. Here ADC sampling, This diagram explains the complete workflow of the project. The sensor collects the information from the vehicle. STM32 Blue Pill microcontroller processes the sensor data and calculates the important parameters. The ADAS module checks all nearby obstacles and possible collisions. Finally, all the processed information is sent through the UART communication to Python dashboard where it is displayed in the real time. This is the system works in terms it is overall data flow what is going in our project. And then we have state transitions which are under a state mission. The vehicle operates through different states such as park, ready, driving, generative braking and fall. These are all states we have. The hardware mainly consists of the STM32 microcontroller, ultrasonic sensors we use, LEDs we are using, and we are using an best communication protocol, UART communication protocol. Together, these components helps in monitoring the vehicle and implementing the safety features. And then we have hardware design. We used ADC, analog to digital converter, UART. Because why we use means we are getting sensor data as analog, right? It's content, so we have to change it to the discrete. So we use the ADC component, UART communication, and we use ultrasonic sensors to calculate the left, right, and front distances, collision situations, and we use the LEDs to showcase false, right? We have to identify it, so that's why we use it as an output device as LEDs, and these are all we used. We have alarm software, then we have software modules, separate module files, EV control. We use we everywhere when we code, like we have to code some bulk project means we have to divide it to part by part, then we will complete step by step and all. Like that only we have EV controller.c, which in where we calculate the speed, SOC, torque and driver's modes, and all will be controlled by the EV control. ADAS.c TT, we here we call time to collision will be calculated. Sorry, time to collision will be calculated. Blind spot logic, all these will be there. ADAS.c. Ultrasonic.c, ultrasonic sensors sensing the distance coming from there and sending it to the UART, and all will be there. Fault, as usually fault flags and the state transitions will be there. UART cell and UART packet topics will come. Its metrics it will send byte by byte. I will show while I am executing. I will show all the file names in my coding part. I will show everything over there. You can understand better. And then we have alarm and collision acceptancy. Here dashboard color coding is the green, it means a normal, no error will be there. And it is yellow, but here type error yellow is a warning, and red color critical. You go like that we will have designed our EV dashboard. Then accept criteria you can see there, published within the 10 seconds of the power on, and if options are changing and all will be there. This is the software is divided into separate modules of vehicle control, ADAS, fault management, and communication. The system uses different alarm levels to notify the driver depending on the severity of the situation. So you know, right? If the situation is more critical, means it will stop and everything will be detected. If some cases like that, we are giving priority to main, to safety. That's why we are all implementing this. Overall, the project successfully achieved its objective of combining EV monitoring with driver acceptance. Then we have this is only now that I have explained the complete EV dashboard system. I will move to the second presentation, which is focuses on the dashboard, EV dashboard. I will go. Sorry for the delay. I will present this. Here, the dashboard is designed to display all the important vehicle information in one place. You are all also aware of the EV dashboards, right? We have seen our electric vehicles such as motorcycle. We have electric EVs, bikes, scooties are there. We are all aware of that, and we have cars also nowadays. All are EVs only. We have here problem statements. First, I have to say this, but now I am saying modern EVs generate to enormous real-time data, speed, SOC, torque, temperature range. Without a centralized dashboard, engineers cannot monitor performance and ADAS safety simulations. Collisions, blind spots, and the fault may go undetected. Without having this, we can't say if normal vehicles also are there. What is less means everything is under the control of the driver. If driver have those all safety measures, okay. In our system, even the driver, if somewhere our we are going okay, if another vehicle coming from left side has too much closing, but we are moving ahead, then our system ADAS system will help over there. We will get an alarm and we have to take that measures. If even though closer, it will take accordingly decisions. The solution is real-time speed SOC range monitoring, ADAS collision and blind spot detection, motor temperature and fault alerting, live Python dashboard UART, third alarm system, drive mode control. These are all will help in such cases. And then we have architecture, system architecture. Here, this dashboard receives data from the STM32 through STM, which is an microcontroller. We can use another, but it is useful and more portable to use through UART communication. The Python application processes this information and updates the display in real time. Here we have all used the sensors, STM32 Blue Pill microcontroller, UART protocol, Python dashboard, as you know. And then we have real industry versus our project. Real industry potentiometers versus PiximLab. We used here PiximLab software which we can implement the all over hardwares in that, because this is an online presentation, right? We cannot currently we are not having hardware, and it is also an opportunity to check. We simulate all in the software. Even we build an hardware in a PiximLab software, and then we simulate. Then we will push our code, and everything will be hardware. If we simulated correct in software, means it will go right. We have some limitations. We will check there. Like that, we will go all over these, and then we have 9 phases of our project. First one is developing our environment. We use several environment, which means our software. We use for coding, we used STM32 QID. Here we code everything, and then we will generate a binary file or hexadecimal file, and then we will push it into the hardware, which is a microcontroller, which we implemented in the PiximLab software. And then we in PiximLab we getting UART and all, we send those data using UART protocol to the Python dashboard, our main dashboard, which can visible to humans and all. You non having technical knowledge also can understand through that EV dashboard. And then we have GPI paraphels, buzzers, we use timers, interrupts, LEDs, and sensor inputs for here we using software, right? We have not implementing it on cars, right? That's why we are using the potentiometers as an accelerator pedal, brake pedal, and temperature pedal. And also one more is there, motor pedal also is there, but it is not SOC also is there, temperature SOC, because we are not implementing it before. We have to check, right? With potentiometers we can increase it and decrease you while executing, you can understand. And then we have EV dynamic model where speed, torque, SOC, range, drive modes and all will be calculated. There will be a lot of formulas which are not required. Anyone can get through online also. I will show, that's also I will show. Then we have ultrasonic ADAS, TTC, BSD, left side, blind spots, all will be calculated. Fault alarm system, we have UART telemetry, we have UART shell, we have Python dashboard and all we have. And then we have our ADC sensor plus EV dynamics, torque, speed, SOC. These are all same as usual. We implemented here motor temperature from 0 to 120 max. Okay, so okay. Brake 0 to 100, accelerator 0 to 100, and SOC is also there 0 to 100. You can see while executing 2 kilowatt, and here all we given some parameters. On phase 5 we have ultrasonic ADAS engine. FCW means it's felt front collision warning will be generated. We have alarms and warnings, right? These will be generated on these bases we presented in this PPT. These conditions we are given in the code, which means front collision will be warning will come when the distance, that means our vehicle and front vehicle will have a less than of 50 centimeters, then will be the warning collision will come, and it will be taken treated. Our Blue Pill microcontroller will treat it as critical when the distance will be less than of 20 centimeters, and then critical it will stop. You will see while executing also the time to collision is there, blind spot left and right blind spots are there, parking assistance, overspeed also they will not, advisory alarm will also oh, triggered when our speed will be overspeed, that means greater than 120 kilometer per hour. And we have uh, fault and alarm and UART telemetry. I have explained this before also. Normal means zero means normal operation. Adversary means if speed or blind spot, it will be okay. Somewhat we can escape, like alarms will be the adversary, and warnings will be uh, too close and 250 kilometers. And then we have critical alarms also, different types of alarms to ensure the different. And then we have UART shell plus Python dashboard. Here we have set as speed we considered in kilometer per hour set vehicle speed, and SOC we have range of 0 to 100, and speed also its maximum is 120 and minimum we have known that 0. And then modes are eco, normal, sport, and we have fault reset status and all. Here in Python dashboard we have speedometer, SOC bar, speed history, EV metrics, and ADAS bar. You will see while I am executing, you will all get to know there. Okay, and then results and demo. I will show everything how we executed and how we built. We will come to know what are the result and what we have to know. Speed and SOC speedometer will be there, 10 FPS, and associate drain currently recovers under the recent ban. Blind spot monitoring, left and right blind spot monitoring will be shown. Collision detection will be there. Over temperature fall, that means a motor temperature will be rising at a maximum range. Then we have to take care, right? That's why we keeping this all. And we have a Python dashboard and UART cell. Okay, this is my 1 second. Oh, okay. These are all my PPT presentation representation, and then PowerPoint presentation, and then as final, I will show how we build and how we executed. For that, first we have STM32 Cube ID where we built everything. That means in coding part. Here we have IOC. IOC means input output configuration. First we have to do input output configuration. I will say we have LEDs, alarm LEDs. What are they? The outputs, giving output. And we have sensing. That means we are using the ultrasonic sensors, right? We are sensing distance by using ultrasonic sensors. Those are giving input to the microcontroller. That means which is a blue pill. And the LEDs are taking the data which are outputs. Those like all configurations will be made over this. Now you can see we have built a EV dash file. These are all ADC and all we did it in earlier days. We learned fundamentals and then and at the end of the project we built end of our internship journey we built all this. In EV dash there are binaries and all. Here we can see this is an IOC input output configuration which I said earlier. We will build all this, and clock configurations we will do here. I have done this before. It is quite complex, but if you think you can do it everything. And then we have, I am showing our code. Here we had ADAS.c. We implemented ADAS configurations and all here, and we have EV controller. Here also included. Here we have header files and all, and we created all header files. EV control fault is here, and then main header file, UART shell, communicating protocol, which sends the data bit by bit, and all header files we created in include header file area. And then in source files we created ADAS. Everything will be source files. It is quite big one, right? We have to code it separate everywhere, but it is my first time I'm explaining everything. And then here, in our main code we included all the header files, and then we call all functions over here. You will see here is print status. We have function definition in there. What? And then we will call here, we will get over all these. Like that we have all coding part over here. And then after building everything, we can go for the build project. You can see here 0 errors and 0 warnings I got. That means, oh, all of my code didn't have any errors and anything. I got all these things successfully. And then we will go to the Pixim lab, which is I already configured, where we will load the binary file of our, just we generated, right? Binary file will be generated, and all we will do, and then we will go to the spare parts of this. Oh, I will bring it to the center. Here we have, this is friend distance ultrasonic sensor. This is an ultrasonic. These are three ultrasonic sensor which are used to calculate the blind spots, which are left, right, and front blind spots. We use it, right? It is, these are potentiometer ultrasonic sensors we can calculate, I think. And then we have potentiometers. For one is for speed, that is acceleration pedal. One is for acceleration pedal, and another one is for brake pedal, and this one is for the SOC, state of charge, which shows our battery life and all. And this is for motor temperature. We are implementing everything in software, right? That's why we are taking, these are potentiometers to give our acceleration, which is an, if we implement it in a car or an electric vehicle, we will not give it to the potentiometer. We will use another sensor to measure those speeds and all. Here we have alarms, like we used this for the fault detection, right? We have this. If there is a front collision will be going to occur, then we have a front collision. This is collision front. And BSD left means left blind spot and right blind spot, and motor temperature fault is it. This is a buzzer, and this is our virtual terminal. I will open this IO virtual terminal term IO virtual term. Sorry. Here we will get, right. You can see every reading will be there. I will clear it once. You can get to know whether I am getting the readings or not. You can clearly see I am getting the readings, and I will open now. This is my Python dashboard. I will show you the output side by side. By keeping side by side, you will, sorry, I removed the spare parts and I will include once again. You can get modules, spare parts. Yes, we got them, and I will keep it this side, and this one is this side. I will move all this to this side. As you see, first I will go for the friend distance. I am decreasing the friend distance. Here we got the collision alarm. You can see here we have a less than distribution, and you can see there is a blinking of our dashboard, which buzzer also. You can't record. I am screen recording, right? You can't hear the buzzer. I will increase the font. You will see, and then alarm and fault also gone. And then I will go for the left. You can see there was another vehicle coming close, and it's showing it will show an alarm. It will take some time because we have to send it right. Here our protocol is sending right. Let's see why. It has some delay in time. I will show 1 second. I will increase my motor temperature. You can see there is an alarm motor temperature detecting purpose, and where our dashboard is here. Where is my alarm? I am getting 105. It's not in the range. If we increase furthermore, you will get right. It is quite clumsy. I will open once again so that you can understand quite better. I am going to close everything. I'm going to close. Sorry. I'm gonna close PiximLab, our command prompt, how I opened. You can't understand, right? Just because of I am showing you, you can't understand. That's why I will show from the beginning. First of all, I am going to my dashboard folder, EV dashboard folder. There we have C project. Then I will open my STM cube ID where I will launch it. It will take some time. Okay, I got everything, and then I will go to my V dashboard and I will build my project. Here you can see 0 errors, 0 warnings, no error is there. And then I will go to PiximLab. Sorry. Then I will open my PiximLab. Here I will load my binary file, ev-binary. I am loaded, and I will go for my spare parts. Here you can see there is an alarm. I will stop it, and I am getting all the values for this is okay. And then I will go to VSC tool. I forgot to say about this VSC tool. Here we provide the virtual page for the COM1 and COM6. In my PiximLab, maybe it's COM6. I will go to configure. Here you can see it is COM1. Sorry, I am saved. I will close all this. Then I will come to our command prompt. I will open it. We have to give here path of our file, so that I am going to my file path, Python file path. This is my path. You can see users Bingy, OneDrive and all. This is my path. I have also run it as administrator because sometimes it's not gets issues. That's why I am opening, and I will change my directory to where users, but it is Windows, right? We have to go back. Cd dot dot will go back, then cd dot will again go back, and then I want users. Where is users? C drive, users, CD users, and then we have users. After we have bingy. I will go to bingy, and then I have OneDrive. OneDrive. Where is my OneDrive? Here it is, my OneDrive. And then I will go to my desktop, and I will go to Emertxe internship folder, and then I have Python. Now I have to write a command for executing. I have saved over here. I am just copying and pasting. You can see before Blue Pill has COM1. Now I have to pair it with what? COM6, because we are providing virtual pair for which comms? COM1 and COM6. That's why we given over there. And then we have to give the name of our file, which is ev dash. I given, and I will click on enter. You can see our dashboard is running. Here we clearly see we are getting signal and breakage 10% and all we are getting. Now I will show spare parts part. It will quite difficult to you. Now I will show how the collision will occur. This is what? Right. Here you can see there was collision coming. While if I increase my motor temperature, here error coming. Here see, alarm also getting hit. Like this we have all the temperature, all the pedals. Here we can get speed, and here we have SOC temperature and all, and getting front, left, right, and all collisions. Here we have this, and the speed history also here there. Like this is our final report of our ADAS dashboard system project. And once again, I have to say thank you for the company Emertxe for giving this great opportunity to learn something great and build something great. This is my first internship, and I had a great learning experience, and I'm so glad to get opportunity like this. And I will increase it this, and I will also get rid of my collision part. Once again, I want to thank Emertxe for giving this great opportunity, and I also say everyone seeing this video get an opportunity in another cohort. They're providing an excellent opportunity to build something and to learn something great. That's all. I had thank you slide or not. I will open it here. Thank you. And finally, thank you all for viewing this video. If you have get any doubts, comment it below. Thank you all. Thank you, Emertxe. Thank you, madam. I don't have ever. Okay, thank you.